You've been told your whole life that the universe is full of stars, full of planets, maybe full of civilizations. So why, in all this time, has nobody ever reached you? But before we continue, please subscribe to the channel to give your support. Let's continue. How can aliens ever realistically reach you when just crossing your own galaxy would take longer than the age of the universe many times over? That's the first problem. Distances so big they quietly break your sense of what far away even means. You live in the Milky Way, a huge disk of stars, gas, and dark matter about 100,000 light years across. 1 light year is the distance light travels in 1 year, about 9.5 trillion kilometers, roughly 6 trillion miles. So 100,000 light years is a 1 with 21 zeros after it in meters. You can write that number down, but your brain, my brain, nobody's brain actually sees that scale in any useful way. So let's stick to something you do understand, like a car. Say you get into a car and lock the speed at 100 kilometers per hour, about 60 miles per hour, and you never stop. No fuel stops, no bathroom breaks, you just go forever. At that speed, to cross the Milky Way once, from one edge straight across to the other, would take you more than 1 trillion years. The universe itself is only around 14 billion years old. That means your drive across the galaxy would last roughly 70 times the age of everything that has ever existed so far. Now plug aliens into that picture. If a civilization is on the far side of the galaxy, they're not far like another country or even another planet. They're far like a different chapter of cosmic history. By the time a slow ship from there could reach here, their star might have changed, their biology might have evolved, their culture might have risen and collapsed multiple times. Already, before engines, before warp drives, before any sci-fi ideas, the geometry alone turns "let's visit that other star" into a once-per-civilization gamble. So maybe you say, fine, the whole galaxy is crazy big, but we don't have to think about the whole thing. What about just the closest step, the nearest star? That has to be more reasonable, right? The nearest star system to you, Alpha Centauri, is about 4.37 light years away. In normal units, that's around 41 trillion kilometers, roughly 25 trillion miles. It sounds smaller than 100,000 light years, but 41 trillion kilometers is still way beyond any travel you've ever done. The fastest object humans have ever thrown out of the solar system, Voyager 1, cruises at about 17 kilometers per second, around 38,000 miles per hour. That's much faster than a rifle bullet, faster than any jet, faster than anything in your daily life. Even at that speed, if you aimed Voyager 1 exactly at Alpha Centauri, it would take over 70,000 years to reach it. 70,000 years ago, your own species was still using stone tools. No writing, no cities, no internet, nothing. A trip to the nearest star using the fastest thing you've actually built is longer than the entire history of human civilization, from caves to smartphones. Now flip that around. If aliens near Alpha Centauri had Voyager-level tech and they pointed something at us, they're looking at the same crazy travel time. Even if they are 10 times faster or 100 times faster, you're still talking about journeys measured in thousands of years. For them, let's go check out that little blue planet is not a weekend trip. It's an epic, multi-generation commitment. You might still push back and say, okay, but Alpha Centauri is just one star. Maybe the local area is packed with options, like a dense neighborhood where there's always another stop close by. That would be nice, but the numbers don't back it up. In the part of the Milky Way where your sun lives, the average distance between stars is a few light years. That means between each star, you usually have tens of trillions of kilometers of almost pure emptiness. There is no highway of stars, no convenient chain of outposts every few million kilometers. It's not like driving from city to city, it's more like trying to cross an ocean where each island is separated by distances so big that every crossing is a full-scale space program, not a quick hop. So, for any aliens, every step between stars is a major operation. You're not just loading up a small ship and cruising over. You're building something that has to survive decades, centuries, maybe longer, in deep space, with no resupply, no repair station, no safe harbor. Our entire space history, every rocket launch you've seen, is tiny compared to what even one serious interstellar mission would need. And here comes the next problem in a very direct way. Even if they can build ships that handle those distances, they still have to know where to go. And that's where you realize how small your planet really is. Earth orbits its star about 150 million kilometers out, around 93 million miles, and the Sun itself is sitting about 27,000 light years from the center of the galaxy. The Milky Way has hundreds of billions of stars. Earth is one rocky planet, around one average star, in one spiral arm among all of that. If you shrank the whole galaxy down to the size of a large country, the region you live in would be something like dust on one random patch of ground. From the alien point of view, they're looking at a disk of stars, gas, dust, and dark matter tens of thousands of light years across. And inside that, they have to notice a small, faint, bluish planet that has only been clearly technological for maybe 100 years. Finding you is not like seeing a bright lighthouse. It's like trying to pick out a tiny pixel in a noisy image from a huge distance. And that pixel is orbiting a star that is also moving through the galaxy at about 220 kilometers per second, roughly 490,000 miles per hour, while all the other stars move too. So from far away, Earth is not just small, it's small and moving. And your entire "we're here" signal, your radio and TV and radar, has only had about a century to spread out, which means a bubble maybe 100 light years in radius, inside a galaxy 100,000 light years across. That bubble is basically nothing, a thin shell of weak radio noise that gets swallowed by the natural radio hiss of the galaxy very quickly. At this point, you might say, sure, this all sounds bad, but tech improves. We improved fast. Aliens could be millions of years ahead. They could have solved this. That sounds reasonable, until you look at how our own progress actually compares to the distances involved. In about 60 to 70 years from the first orbital rockets to our fastest interstellar probes, human launch speeds have gone from about 8 kilometers per second to about 17 kilometers per second. That's a little more than a factor of 2. It's a big deal for engineers, but as a fraction of light speed, it's tiny. Light moves at about 300,000 kilometers per second, so our fastest probes are doing a bit less than 1/10,000th of that. Now, look back at the fixed distance to Alpha Centauri, around 41 trillion kilometers, and to the far side of the galaxy, around 9.5 quintillion kilometers. Those distances don't shrink. No matter how clever your computers get, no matter how good your materials get, the gap you have to cross stays brutal. Each small gain in speed shaves a little off the travel time, but you start from a base that is so huge the universe barely notices your effort. So here's the core point of this whole first step. Before you talk about weird engines or warp drives or alien motives, the raw scale of the Milky Way already pushes visit Earth physically into the category of something that might, at best, happen once in the entire lifetime of a civilization if they are insanely determined. For normal, practical planning, for any species that cares about resources and risk, the galaxy's distances alone make casual alien visitors to Earth effectively impossible. And this is only level 1 of the problem, because even if someone out there is crazy enough to try and rich enough in energy to launch a serious ship, they're about to slam into another wall that doesn't care how advanced they are. There's a maximum speed built into the structure of reality itself, and as you push closer to it, the cost and energy explodes, the returns shrink, and every plan to just go faster starts to fall apart. So the next question is simple and brutal at the same time. If the distances are already this bad at normal speeds, what happens when you add the hard speed limit of the universe on top of that? So space is huge, you've seen the numbers, but you might still think, fine, just go faster. Here's the uncomfortable part. There's a hard speed limit built into reality, and it does not care how advanced you are. There's one number in physics that acts like a brick wall, about 300,000 kilometers per second, roughly 186,000 miles per second. That's the speed of light in a vacuum. If you have mass, if you are made of anything, you never get to hit that number. You can get close, you can shave off decimals, but you never touch it. The closer a spacecraft gets to that speed, the harder the universe pushes back. Your energy bill doesn't rise in a straight line, it explodes. Doubling your speed doesn't mean doubling your energy. It means multiplying it by huge factors, because speed is squared in the energy formula. Engineers describe it in math, but in normal language, every extra step toward light speed costs you more than the step before. And this isn't just a theory on a blackboard. We have tested this in particle accelerators, in space probes, in atomic clocks on planes and satellites. Tiny particles at places like CERN are pushed to more than 99.9% of light speed, and every time, relativity predicts exactly how much energy you need, how their clocks slow down, how their effective inertia rises. We never see a particle suddenly decide, you know what, I'll just break the limit today. No loopholes, no weird edge cases, nothing. So if there is a speed wall at 300,000 kilometers per second and pushing close to it gets brutally expensive, what happens if aliens play it safe and aim for a slow fraction of that, something like 10% of light speed? That sounds reasonable, right? Not crazy, but still unbelievably fast. Take 0.1 c. 10% of light speed. That's about 30,000 kilometers per second, around 67 million miles per hour. Compared to your rockets, that's insane. The fastest human spacecraft crawl at a tiny fraction of that. A ship doing 0.1 c would cross the distance between Earth and the Moon in just over a second. In the solar system, it would be like skipping stones across a pond. But zoom back out to interstellar scales again. At 0.1 c, that nearby star system, Alpha Centauri, is still more than 40 years away, one way. And that's ignoring the time you need to accelerate up to that speed and then slow back down. So you're looking at maybe 50 or 60 years for a realistic trip profile, in the best case. That's one mission to the nearest star with heroic engineering. Now take the far side of the Milky Way. At 0.1 c, crossing the galaxy still takes on the order of 500,000 years, 500,000 years for one crossing, at a speed that makes our current technology look like stone tools. Even when you give aliens sci-fi engines and generous assumptions, the galaxy refuses to shrink. It stays hostile in the one way that really matters: travel time. So you could say, all right, time is bad, but maybe they don't care about time. Maybe they're patient. What does it cost in raw energy to run at those speeds? That's where the situation goes from hard to, are you serious? Take a modest starship, nothing like a huge city in space, just a solid, serious vehicle with a mass of around 1,000 tons. That's about 1,000,000 kilograms, similar to a large ocean ship or a decent skyscraper chunk. To get that mass up to 0.1 c, you use the basic kinetic energy idea. Energy equals half the mass times the speed squared. In words, you cut the mass in half, then you multiply by the speed times the same speed again. When you plug in 1,000,000 kilograms and 30,000 kilometers per second, the number you get is around 4.5 times 10 to the power of 20 joules. You don't need to memorize that. What matters is the comparison. That amount of energy is roughly equal to all the energy humans currently use in a year. Every power plant, every car, every plane, every factory rolled into one single burn. And that's just to accelerate. You have to slow down at the other end unless you want to scream past your target star and vanish into deep space, so double the bill. And that's before you talk about engine inefficiency, heat losses, maneuvering, or emergency reserves. In practice, the real energy demand is worse. Any civilization trying to visit one random star at 0.1 c is setting fire to a planet-scale energy budget just for that one attempt. Now, remember, 0.1c is the sensible fraction of light speed. What if aliens aim higher, say 0.5c, half the speed of light, or 0.9c, or 0.99c? Then they can really compress travel times, right? Ride that time dilation, get to distant places while less time passes on the ship. That sounds clever until you look at how the costs explode. As you push toward these higher fractions, relativity adds a nasty twist. Your effective inertia rises, which you can think of as your relativistic mass going up. The faster you go, the more energy each tiny extra bit of speed demands. Going from 0.1c to 0.2c is already a huge jump in energy. Going from 0.9c to 0.999c or 0.99c to 0.999c is like climbing a vertical cliff. Every centimeter forward costs you more fuel, more reactor output, more everything. We see this directly at particle accelerators. Protons near light speed soak up enormous amounts of energy, but their speed barely increases. Most of the extra energy goes into changing their internal state and time behavior, not into pushing them any closer to the forbidden speed. That's why even at facilities with insane power usage, we never see a proton hit or exceed light speed. They asymptotically creep toward it. So for aliens, the let's just go much faster option is not free. Every step toward 0.9c, 0.99c, 0.999c multiplies the energy bill, the engineering requirements, and the shielding needs. You can do the math in different ways, but the qualitative story is the same. Truly high relativistic speeds destroy your energy budget. That kills the idea of casual tourism. No one is going to spend star-level resources just to drop by a random blue dot for a quick visit. At this point, you might reach for the usual sci-fi escape hatch. What about faster than light, warp drives, hyperspace, wormholes? Can't an advanced species find a clever way around this speed limit, something that lets them jump the queue? It sounds tempting, but reality is not giving us any hints. If faster-than-light travel were easy, or even just moderately possible, you'd expect relativity to show cracks. You'd see weird timing glitches in satellite systems, strange mismatches in atomic clocks, or unexpected behavior in high-energy particles. But every precision test we have done, from GPS systems that rely on relativity corrections to stay accurate, to long baseline clock experiments, to cosmic ray observations, keep telling the same story. The rules hold. Space and time behave exactly the way special and general relativity say they should, up to ridiculous levels of precision. Theoretical ideas like warp drives or traversable wormholes need exotic forms of matter with negative energy density, stuff we have never seen in nature. They're not just hard engineering, they're maybe not even allowed territory. So any alien civilization that wants to beat the light speed limit has to either discover new physics far beyond what we have and somehow make it practical, or accept the same hard ceiling we do. So here's the bottom line of this whole section. Relativity does not care how old, rich, or advanced you are. If you have mass, you are stuck under the speed of light, and as you get close to it, the energy cost rises brutally. Even at 10% of light speed, reaching your nearest star is a lifetime mission. Crossing the galaxy is a 500,000-year project. In realistic terms, let's pop over to Earth turns into a deep-time expedition with civilization-scale resources on the line. And this is still not the end of the trap, because even if aliens somehow pay that energy bill and accept those travel times, there's another layer waiting, the rocket equation itself, the way propulsion works, which punishes every kilogram of fuel, every piece of shielding, every attempt to push harder. If the speed limit is the wall, the rocket equation is the troll at the gate, demanding an impossible fuel payment for every extra bit of velocity. You've seen the distance problem and the speed limit, so why not just build a bigger rocket and brute force it? That sounds simple, but this is where the universe brings out another cruel rule, the rocket equation, which basically says, every time you want a bit more speed, I'm going to charge you far more fuel than last time. Every rocket you can build and every rocket aliens can build has to follow the same basic logic that Konstantin Tsiolkovsky wrote down over a century ago. In normal language, it goes like this. Your total possible change in speed depends on two main things: how fast you can throw exhaust out the back and how much heavier the rocket is when it's full of fuel compared to when it's empty. That second part is your mass ratio, full mass divided by empty mass. Here's the nasty detail. The relationship isn't linear, it's logarithmic. That means when you want a little bit more speed, you don't just add a little bit more fuel, you have to multiply the fuel. The first chunk of speed is cheap, the next chunk is expensive, the next is brutal. If you say, I want 10 times more total speed than before, the fuel requirement often explodes into ridiculous territory, where your rocket becomes almost nothing but fuel tanks. This is why our current rockets already look so extreme. A typical orbital rocket is mostly fuel by mass, with just a tiny payload on top. And that's only to get a few kilometers per second of speed, maybe around 8 or 9 kilometers per second, which is enough to reach low Earth orbit. That's nothing compared to what you'd need for a serious fraction of light speed. So let's look at what we actually use today. Chemical rockets. How bad are they really if you try to go to the stars with them? Chemical rockets, burning things like hydrogen and oxygen, or kerosene and oxygen, throw exhaust out the back at maybe 3 to 4 kilometers per second, roughly 7,000 to 9,000 miles per hour. That's fine for launching satellites, space stations, even missions to Mars if you push it. But for interstellar travel, those exhaust speeds are hopelessly low. If you try to reach even 1% of light speed with that kind of exhaust, so about 0.01 C, around 3,000 kilometers per second, the rocket equation goes insane. To get that much total speed out of that slow exhaust, your mass ratio has to be enormous, so big that your spacecraft ends up being something like 99.9999% fuel and a tiny fraction of a percent useful payload. You basically build a giant fuel tank with a little capsule glued on the front. There's no room left for thick shielding, comfortable habitats, or a big alien crew. So chemical rockets, the tech we actually know how to build and scale, are already dead for serious starflight. They work around planets, they work inside a solar system, but beyond that, they hit a hard wall. If aliens rely on chemistry, they're not going interstellar in any crude, meaningful way. You might say, fine, skip chemistry, use the big guns, go nuclear. That's the next obvious step, and it does help, but not in the way sci-fi makes you think. Nuclear thermal rockets heat a propellant, usually hydrogen, with a nuclear reactor and push it out at higher speeds, maybe 8 to 10 kilometers per second, around 18 to 22,000 miles per hour. That's a solid improvement over chemical, about 2 to 3 times better exhaust velocity. Nuclear pulse concepts, like the old Project Orion design, don't just heat gas, they literally drop nuclear bombs behind the ship and ride the blast. And in theory, those could get you a noticeable fraction of light speed. But now look at the price. A nuclear thermal rocket is a flying reactor that has to run perfectly for years in deep space. A nuclear pulse ship is a machine that needs thousands, maybe millions of nuclear charges, stored, handled, and detonated with absurd reliability. You've turned your Starship into a multi-megaton bomb platform operating for decades or centuries. The engineering is insanely hard, and the safety issues are off the charts. And even then, the rocket equation does not go away. You get a higher exhaust speed, so your mass ratio problem is a bit less crazy, but it's still there. You still have to trade mass ship versus fuel mass and payload mass. Want more shielding to survive radiation? That's extra mass. So you either accept lower speed or you add more fuel, which adds more mass, which demands even more fuel. It's a vicious loop. The more you try to make the ship actually livable and safe, the more you wreck the performance. So even with nuclear tech, even with near-perfect engineering, you end up with an ugly trade-off. Do you want speed or do you want comfort and safety? Picking both pushes you into a region where the total cost is so high that sending big crewed ships just to visit some random planet like Earth becomes economically absurd. At this point, you might try another angle. What if you don't carry the fuel with you at all? What if you leave it at home and push the ship with light or particles like a sail in a beam? This is where beamed propulsion comes in. The basic idea is you build a giant laser or microwave array near your star, you aim it at a huge thin sail attached to the ship, and you push the ship by bouncing photons or particles off that sail. The ship stays light because it doesn't carry fuel, but now the home system has to pay the full energy cost. On paper, this can get small probes up to a good fraction of light speed, but on paper is doing a lot of work here. In practice, to accelerate even a small payload, you're talking about laser powers in the gigawatt to terawatt range, billions to trillions of watts, running for long periods, focused into a narrow beam that has to stay aligned over millions or billions of kilometers. If you miss the sail by a tiny angle, the beam just flies off into space and your ship drifts uselessly. This means any aliens using beamed propulsion need insane infrastructure at home. Giant power stations orbiting their star, massive focusing optics, advanced control systems all dedicated to launching maybe a few gram-scale or kilogram-scale probes. Scaling that up to a huge, heavily shielded, comfortable crewed starship is another huge jump in difficulty. The sail would have to be enormous and perfectly controlled. The beam power would have to rise even further, and any slight mistake could destroy the ship. So yeah, you dodge onboard fuel, but you move the problem back to the home system, which now has to pour star-level energy into each mission. It doesn't make things easy, it just changes who pays the bill, the ship or the sender. And even once you've picked a propulsion method, you hit the final practical constraint: how you use your mass. Every kilogram you put into shielding, life support, spin decks for artificial gravity, water, food, backup systems, entertainment, anything to make life sane for the crew, is a kilogram you are not putting into fuel or into a lighter, faster design. A real interstellar ship, designed by serious engineers, is not going to look like a luxury cruiser. It will look like a stripped-down, tightly optimized tube where every gram is tracked. If you want heavy radiation shielding, that slows you down or forces a bigger engine. If you want big habitats with room to walk and live, that's more mass. If you add redundancy for safety, more mass again. The rocket equation punishes all of it. So, from the point of view of a civilization that has to manage resources, the question becomes painfully obvious. Why pour this much effort into sending a fragile, heavy, crude vehicle to one random planet when you could use the same energy to build more stations, more habitats, more technology around your own star? Staying home gives you guaranteed benefits. Sending a ship gives you a tiny chance of some science data and a lot of risk. Put simply, the rocket equation doesn't just make interstellar travel technically hard, it makes large, comfortable, casual, crude visits to Earth almost irrational. It pushes any sane species towards smaller, lighter, unmanned probes, or toward not bothering at all. And even if some civilization is extreme enough to fight through all of this, build the engines, pay the energy cost, and accept the brutal design compromises, they still have another layer of reality to face. Between the stars, the environment itself is hostile. The medium is thin, but not empty. And at high speeds, even a speck of dust can hit like a bomb, while radiation slowly eats your ship from the inside out. So the next problem is simple. If you somehow get a starship moving and you somehow feed it, can you even keep it alive when deep space is actively trying to kill it every second of the journey? You solve the engine problem, you pay the fuel bill, you launch your starship at a serious fraction of light speed, and then space itself starts trying to tear it apart second by second. That's the next big hurdle. Deep space is not a calm, empty highway. It's an environment that slowly grinds everything down. People hear vacuum and think nothing, but between stars there is still matter. On average, you get about one hydrogen atom in each cubic centimeter of space. That sounds like basically zero compared to air at sea level, which has something like 10 billion molecules in the same volume. But now, combine that thin gas with high speed. At zero point 0.1 C, 10% of light speed, your ship is plowing through space at around 30,000 kilometers per second, roughly 67 million miles per hour. Every single hydrogen atom you hit slams into your hull with serious energy, because energy rises with the square of speed. One atom is nothing, but over light years of travel, the number of impacts is huge. That adds up to a constant microscopic sandblasting of the front of your ship, constant heating of whatever material is sitting at the nose. So right away, an alien starship needs a sacrificial shield facing into its direction of motion, something it can afford to erode over time, and a thermal system to dump the heat from all those tiny impacts. If you don't overbuild that front end, the hull slowly wears away. If you do overbuild it, you add mass, which pushes your propulsion problem back up. And that's just the gas. What happens when you hit something bigger than a single atom? Space also contains dust, little grains of rock or ice, from nanometers up to micrometers and beyond. A 10 micrometer grain, something like fine smoke particle size, is still tiny by human standards, but smack into that at zero point 0.1 C, and the kinetic energy released is like a rifle bullet, or worse, concentrated into a microscopic spot on your hull. You are not dealing with one impact. Over millions or billions of kilometers, your ship is going to hit a lot of these grains. Each one punches a crater, spalls off fragments, sends shock waves through the material. Without very thick shielding or some kind of active deflection system, your hull gets sandblasted into scrap over time. The outer layers crack, flake, and erode. Joints weaken. Sensors and radiators on the front side are at constant risk. Engineers can try tricks like multi-layer Whipple shields, where a thin outer layer vaporizes incoming particles before they hit the main hull. That works for current spacecraft at current speeds. Scale it to 0.1 C and the required thickness jumps. Suddenly, you're talking about meters of material just to absorb the constant stream of micro bullets. Once again, every extra centimeter of armor is more mass you need to push to a serious fraction of light speed. And that's just the gas. What happens when you hit something bigger than a single atom? Space also contains dust, little grains of rock or ice, from nanometers up to micrometers and beyond. A 10 micrometer grain, something like fine smoke particle size, is still tiny by human standards. But smack into that at 0.1 C, and the kinetic energy released is like a rifle bullet, or worse, concentrated into a microscopic spot on your hull. You are not dealing with one impact. Over millions or billions of kilometers, your ship is going to hit a lot of these grains. Each one punches a crater, spalls off fragments, sends shock waves through the material. Without very thick shielding or some kind of active deflection system, your hull gets sandblasted into scrap over time. The outer layers crack, flake, and erode. Joints weaken. Sensors and radiators on the front side are at constant risk. Engineers can try tricks like multi-layer Whipple shields, where a thin outer layer vaporizes incoming particles before they hit the main hull. That works for current spacecraft at current speeds. Scale it to 0.1 C and the required thickness jumps. Suddenly, you're talking about meters of material just to absorb the constant stream of micro bullets. Once again, every extra centimeter of armor is more mass you need to push to a serious fraction of light speed. So the obvious question then is, even if you armor the hull, what about the stuff going straight through it, the radiation blasting everything inside? High-energy radiation from outside the solar system, galactic cosmic rays, is a constant background. These are mostly protons and heavier atomic nuclei moving at near light speed, far faster than 0.1 C. On Earth, you're protected by the planet's magnetic field and thick atmosphere. Those particles hit air molecules, create showers of secondary particles, and most of the really dangerous stuff gets stopped before it reaches the ground. In deep space, especially between stars, you lose almost all of that protection. Astronauts on the International Space Station already get a higher radiation dose than people on the ground. For long missions beyond low Earth orbit, like a Mars trip that takes a couple of years total, space agencies are seriously worried about lifetime cancer risk and damage to the nervous system. Now, extend that from a few years to decades or centuries on an interstellar mission. The crew is getting hit by high-energy particles day and night every day of the journey. Those particles break DNA, damage cells, and gradually increase the chance of cancer, cataracts, and other problems. Over a long enough time, with no heavy shielding, you're basically slow cooking the crew's biology at the genetic level. And it's not just the crew. Cosmic rays also flip bits in electronics, damage circuits, and slowly break down materials. Your computers, sensors, and control systems are under a constant random attack. You can use error-correcting codes, hardened electronics, and redundancy, but over centuries, the number of hits adds up. So you say, fine, put a lot of shielding between the crew and the radiation. That's the right instinct, and it leads straight into yet another trap. Good shielding against cosmic rays and solar flares usually means thick layers of hydrogen-rich material, like water or certain plastics, or just lots of mass in general, including metals. You're talking about meters of protection around the living areas, not a thin wall. To make a truly safe interstellar ship for a long-duration crew, you might need tens of thousands of tons of shielding mass alone. Go back to the propulsion side. Every ton of shielding is a ton you need to accelerate to 0.1 c and then decelerate. The energy you need goes up directly with mass. The rocket equation punishes you twice. You need more fuel to move the extra shielding, and the fuel itself has mass you need to move. The total ship mass swells, pushing the energy costs into absurd territory. You shift from big ship into mobile megastructure territory very quickly. In practice, then, this means aliens have to make a choice: accept high radiation doses and shorter, riskier mission durations, or accept insane energy costs and engineering complexity to build a heavily shielded, safe vessel. For a civilization that can do basic math, this is not a comfortable trade. Maybe you try to dodge the whole issue by taking the crew out of the equation, at least biologically. Put them into cryosleep or deep hibernation, or upload their minds into computer hardware. Let the ship coast through the danger while everyone is asleep. That sounds like an easy fix, but it doesn't actually change the environment. Even if nobody is awake, the ship is still being hit by cosmic rays, micrometeoroids, and dust. Cryosleep pods are made of materials that can crack and leak. Electronics running uploaded minds can still suffer radiation damage. Memory bits still flip. Structural components still get eroded. Time passing in cryosleep is still time passing for your hardware. Over centuries, plastic becomes brittle. Metals creep and fatigue. Seals degrade. Lubricants dry out or break down. Active systems like self-repairing nanobots also need power and raw materials, and they themselves can fail or mutate under radiation. There is no pause button on physics. So cryosleep may solve the psychological and social problem of a long mission, but it does almost nothing for the physical one. The ship has to survive the entire journey in working order, and the environment it moves through is constantly trying to chip away at it. Deep space is not a neutral background. It's a slow, relentless grinder. When you add all of this to the earlier problems, you get another brutal layer of no. Surviving the journey intact, physically and biologically, is a near impossible engineering challenge by itself. Before aliens even think about slowing down your Earth, entering the solar system, and dropping into our atmosphere. And even if one civilization, somewhere, is extreme enough to beat the distances, pay the energy, fight through the radiation, and keep a starship alive for centuries, there's an extra constraint waiting that physics alone doesn't answer. How long does a civilization itself stay focused and stable enough to support a mission like this? And what does time dilation do to that? How do you keep a mission alive for longer than your own species remembers its history, when the travelers, the people funding them, and the entire civilization behind them all have expiration dates? That's the next problem. Even if the ship can survive deep space, the society that launches it has to survive deep time. Start with something simple: lifespans. Complex animals on Earth typically get decades, maybe a century at the very high end. Humans are in that range, roughly 70 to 90 years if things go well. There's no good reason to assume aliens, made of cells and chemistry, are naturally immortal. Their biology will break down, their organs will age, their repair mechanisms will fail, just like ours. Now connect that to interstellar travel at non-relativistic speeds. If your ship is going at a small fraction of the speed of light, even just 1% of light speed, that's still 3,000 kilometers per second, about 1.8 million miles per hour. It will take hundreds of years to cover even nearby interstellar distances, and thousands or more for anything ambitious. That means a single mission, from launch to arrival, spans dozens of human lifetimes. For many targets, it's hundreds of lifetimes. So the people who start the project are dead long before the ship even reaches cruising speed. The people who maintain the infrastructure are dead. The engineers who wrote the software are dead. Their great-great-great-grandchildren are dead. The mission becomes something that has to be handed down like a legend, a core story of the civilization. We Have a Ship Traveling to That Star becomes less like a project update and more like a myth. Relativity offers a partial escape: time dilation. If you move very fast, close to the speed of light, time on the ship runs slower than time for people who stay behind. At around 0.9 c, 90% of light speed, that factor jumps to around 7. In casual language, for every year that passes on the ship, several years pass back home. Push that even closer to light speed, and the effect gets stronger. The travelers can, in theory, cross big parts of the galaxy and only experience a few 100,000 years on board, while millions of years pass outside. For them, the trip is compressed. Their subjective time is not as brutal as the outside universe's time. But that only helps the people on the ship. Back at home, the civilization that launched them still lives in normal time. If the ship takes, say, 50,000 years in the galaxy's frame to get somewhere, that's 50,000 years of history for the homeworld. Over that period, continents shift a little, climates change, cultures rise and fall, technology transforms over and over, or the whole civilization simply collapses. From the ship's point of view, the homeworld races ahead, evolves, maybe dies, while they are still mid-flight. From the homeworld's point of view, the ship is a long-running background process that doesn't report back for ages, if it ever does. The connection between them stretches, then snaps. Whatever promises were made at launch, whatever expectations existed, can't realistically be maintained for that long. Now look at how actual civilizations behave on Earth. Big empires tend to last hundreds to a couple thousand years at most. The Roman Empire, the ancient Chinese dynasties, the European colonial empires, all of them have lifetimes measured in centuries, not tens of thousands of years. Our entire technological phase, from telegraph to internet, is only a few hundred years old. So it's reasonable to expect that technological civilizations have a kind of half-life. Some survive longer, some shorter, but they are constantly under pressure from wars, climate shifts, resource problems, pandemics, or just cultural drift. Values change, priorities change. A project that made sense 1,000 years ago can look pointless or even dangerous now. Keeping a multi-millennium mission funded, staffed, repaired, and protected from budget cuts or active sabotage is not just a technical challenge, it's a social one. It requires a level of long-term stability we have never seen. And remember, the target is not a guaranteed paradise. It's often just a faint, maybe Earth-like signal in the noise. Think about the motivation side. You have to convince whatever your decision makers are, voters, a council, an AI planner, a hive mind, to spend enormous resources for 10,000 or more years on constructing, maintaining, and supporting a ship that might arrive at a random rocky world that could, by then, be sterile or already occupied or completely uninteresting. Every year, that cost competes with other options: more habitats at home, more computing infrastructure, terraforming nearby moons, improving quality of life. The longer the travel time, the harder it is to justify the mission, especially when every generation that comes after you will ask, why are we still paying for something our ancestors started? What do we get out of this? Motivation decays much faster than clocks. You can correct for engine wear, you can replace components, you can patch software, but you can't easily keep a whole society emotionally invested in a goal that will not pay off for 100 lifetimes. For most civilizations, rational or not, the payoff curve will push them towards spending their energy in their own system, where the feedback is immediate, where the benefits are obvious. And here's the paradox at the core of this section. If you keep ship speeds low to keep energy and shielding demands reasonable, your missions take so long that they turn into myths, and your civilization is very likely to change or fall apart before they finish. If you crank the speed up to get strong time dilation and shorten the subjective trip for the crew, you slam into the crazy energy costs, brutal radiation problems, and engineering nightmares from the earlier sections. So either way, the limiting resource is not just fuel, it's civilizational coherence. You need a culture that stays stable and focused for absurd time spans, while also being technologically advanced and safe from its own self-destruction, and willing to dump star-level energy into a single mission, and willing to do all that for a target that might not care you came. Put bluntly, even if the laws of physics allow a ship to get here, biology, psychology, and basic cost-benefit logic all push against the idea that anyone would bother. The physics doesn't fully forbid the trip, but the sociology makes it vanishingly unlikely. And yet, suppose some civilization is stubborn enough, united enough, and rich enough in energy to ignore all of this, to say we are doing it anyway, and launch a ship across light years. There is still another set of limits waiting for them, not in the equations of motion or in the hearts of voters, but in the materials the ship is made of, in the way structures handle stress, fatigue, and heat over centuries of abuse. If your mission has to last longer than nations and maybe longer than your species, can your metal, your composites, your electronics, and your cooling systems actually hold together that long under relativistic speeds and constant micro-damage? How do you keep a starship from literally ripping itself apart when it's running at speeds your materials were never evolved or designed to handle, for time spans longer than any structure you've ever built? That's the next wall. Even if aliens solve the physics and the fuel and the motivation, they still run into the hard limits of engineering. Start with the basic stress problem. A ship moving at 0.1 to 0.5 times the speed of light, so between about 30,000 and 150,000 kilometers per second, roughly 67 million to 335 million miles per hour, is not just going fast. It is sitting in a constant storm of tiny impacts, internal forces, and temperature differences. Real materials, the stuff you know, like steel, titanium, aluminum, carbon fiber composites, all have tested limits. They handle certain temperatures, certain stresses, certain impact rates, and then they crack, creep, or deform. On Earth, hypersonic aircraft flying at Mach 5 to Mach 10, which is roughly 1.7 to 3.4 kilometers per second, already deal with brutal heating, shock waves, and structural issues. Thermal protection and precise engineering are mandatory, and those flights last minutes, not centuries. Now scale that up by factors of 10,000 or more in speed, and by factors of millions in duration. The front of a relativistic ship constantly absorbs impacts from gas and dust, converting that kinetic energy into heat, while the back might be relatively cooler. Parts near reactors or engines run hot, other parts are shaded and cold. That means thermal gradients, parts of the structure expanding and contracting differently, which introduces stress over and over again. You have to design a frame that doesn't warp, buckle, or fatigue under that continuous abuse. Every joint, every weld, every composite layer has to hold up, not for a few test flights, but for hundreds or thousands of years. That is far beyond any test regime we can run, and aliens face the same basic problem. They still work with atoms, bonds, and crystal structures that get damaged under stress. Then there's the heat problem, which is quietly one of the worst parts of high-power, long-duration spaceflight. Any reactor, any fusion drive, any high-powered electronics rack spits out waste heat. On Earth, you dump that heat into air or water and convection carries it away. In space, there is no air, so you only have radiation. You glow heat away as infrared light. Radiating heat is slow and inefficient, so if you're running star-level power to push a big ship, you need ridiculously large radiators, thin panels that spread out over huge areas, potentially square kilometers of surface, just to keep the core of the ship from cooking itself. These panels have to stay pointed away from the direction of motion enough that they aren't shredded by the interstellar medium, but they also can't be perfectly shielded from impacts. So now you've added giant fragile structures to your design, structures that must not tear, must not twist too much, must not fold up or break off under constant minor hits and vibrations for centuries. They're also glowing in infrared, which means any halfway decent sensor in the galaxy can see your ship as a bright artificial heat source against the cold background. You can't hide a serious interstellar ship. It screams its presence just by trying not to melt. Next, think about fatigue and lifetime. On Earth, you consider a commercial airliner old after a few decades of service, and maybe around 50,000 or 100,000 flight cycles. Cracks appear at joints, metal fatigues from constant pressurization changes and vibrations, and even with maintenance, there is a point where you retire the frame because the risk climbs too high. An interstellar ship is not doing short hops. It lives under constant stress, constant low-level shaking from engines and impacts, constant thermal cycling as systems turn on and off for centuries or millennia. Radiation slowly changes materials' properties, making plastics brittle, introducing defects in metals, turning some insulators conductive. Adhesives degrade, lubricants break down, insulation chars or chemically ages. You can design for maintenance, you can plan for replacement parts and module sections, but that means storage of spare materials, manufacturing capacity on board, and skilled systems to run it all. Every bolt you replace, every panel you swap has to come from somewhere, and there is no quick resupply. You are at least light years away from home, so there's no shipyard visit, no emergency shipment, no fast recall if something fundamental turns out to be flawed. So you might say, all right, let's cheat again. Let's fill the ship with advanced self-repair systems, nanobots, self-replicating assemblers, autonomous factories that can patch and rebuild the ship as it flies. That sounds like the obvious alien move, but it doesn't escape the basic constraints. Those repair systems still need raw materials. They need metals, plastics, semiconductors, all of which you must either carry from home or mine from somewhere along the route. They need energy to run, which comes from the same reactors already struggling with waste heat. They need memory and control systems, which are also exposed to radiation damage and failures. And they have their own error modes, bugs in code, mutation in self-replicating designs, rogue behavior if something goes wrong. So instead of a simple ship that needs maintenance, you now have a complex ecological system of repair units, mini factories, and control AIs, all of which can themselves break or drift from their original design. You haven't eliminated maintenance, you have just spread it out across a more complicated network of things that can fail. So when you pull back and look at the whole engineering picture, what are you really asking aliens to do? You're asking them to build a megastructure made from real matter with real weaknesses. Keep it intact, keep it powered, keep it cooled, keep it repaired, and keep it stable, not for the lifetime of a human pilot or an aircraft, but for time spans longer than your entire recorded history as a species. This is on top of everything else, the fuel requirements, the shielding mass, the radiation environment, the cultural stability. Each one of these by itself is a major challenge. Stacked together, they push crewed interstellar missions out into the extreme tails of what any civilization is likely to attempt. And even if somehow some civilization out there can do all of that perfectly, they build the ship, they keep it alive, they run it for thousands of years, there's still another ugly level. They're not flying through a still, predictable universe. The targets they might want to reach, stars and planets, are moving. Orbits shift. The whole galaxy is a dynamic, chaotic system. So the next question is, if they do launch and their ship survives, how do they actually hit us, a tiny moving planet around the moving star in a shifting galaxy using information that is always decades or centuries out of date by the time they reach them? How do you actually hit something as small as Earth when everything in the galaxy is moving and the only information you have about us is already years or centuries out of date by the time it reaches you? At interstellar distances, just aiming at us is a whole extra problem on top of building the ship. Start with the basic motion. Your sun is not sitting still in space. It's orbiting the center of the Milky Way at about 220 kilometers per second, roughly 490,000 miles per hour. Other stars are doing the same thing, but on slightly different paths, different angles, different speeds. Over millions of years, the whole pattern of stars you see in the sky rearranges itself. Constellations warp and smear out, neighbors drift away, new neighbors move in. So if some aliens detect Earth's radio noise today and they log the position of the sun in their sky, that's a snapshot. By the time they build a ship, launch it, and it actually gets anywhere near us, that snapshot is outdated. We've moved along our orbit around the galaxy, they've moved along theirs. The straight line that connected their star to our star when they first saw us is gone. If they fire and forget, based on that first position, their ship arrives where we used to be, not where we are. Then shrink down from the galactic orbit to the local system. Earth is not glued to the sun. It's orbiting at about 150 million kilometers out, around 93 million miles. On the scale of the galaxy, that radius is microscopic. On top of that, our orbit is not a perfect circle. It's slightly elliptical, it wobbles a bit, and it's influenced by Jupiter, Saturn, and the other planets, plus long-term tidal effects. The exact position of Earth at a given moment is a small, moving target, with small deviations layered on top. So now, the alien ship doesn't just have to intercept the sun, it has to arrive at the right place and time to meet one specific planet that is constantly circling that sun. You're trying to hit a tiny moving target that's orbiting another moving target that's also sweeping around the galaxy. There's no fixed address in space you can aim at and be done. To manage this in any precise way, the ship needs navigation updates, and not just once, but repeatedly. You need to know where Earth is now, then adjust your course, then know where it is later and adjust again. That's normal for any long trip. Even planes and ships do that. But interstellar distances add one brutal limitation. Information can't move faster than light. If your starship is 100 light years away from Earth, the latest signal it can receive from us is already 100 years old when it arrives. That signal tells the crew where Earth was a century ago, what the sun was doing a century ago, what our radio output looked like a century ago. By the time they decode it and try to correct their trajectory, we've already moved on again. So their fresh targeting information is always delayed by the same distance they're trying to cross. To keep tightening their aim, they have to burn fuel, change velocity, and adjust course again and again using stale data. Every correction costs energy. At interstellar speeds, even a small angle change or a small sideways velocity change can mean a huge push. Over a long journey, those course corrections add up and eat into the same fuel and energy budget that was already marginal. If they started with minimal reserves, serious navigation might simply not be possible near the end of the trip. Now add the detection problem on top. Aliens can't aim specifically for Earth unless they first notice Earth. So what are we actually broadcasting to the galaxy? Your strongest artificial signals so far were the early days of high-power radio and TV transmitters and big military radars. Those transmissions radiated in all directions and were powerful enough that, in principle, a very sensitive alien receiver could pick them up from many light years. But those transmissions have only been going on for about 100 years, which means the radio bubble around Earth is only about 100 light years in radius and very thin. The Milky Way is about 100,000 light years across. So your radio bubble is a tiny little sphere inside a disk that is 1,000 times larger in radius. Most of the galaxy lies completely outside any contact with our artificial signals. And inside that tiny bubble, the signal strength drops with distance. It spreads out and gets weaker. By the time it's traveled tens of light years, it has to compete with background noise, the natural radio hiss from stars, gas clouds, and other sources. It gets worse. Modern communications are moving away from loud, broadcast-style radio. You use more fiber optics, low-power, tightly focused beams, spread spectrum techniques, and satellite links that don't leak nearly as much energy into space as old TV towers did. From far away, Earth is actually getting quieter over time in radio. The peak, "Hey, we're here," might already be in the past. So aliens don't just have to hit a moving target, they have to first find that target in a signal environment that's weak and shrinking. They need extremely sensitive instruments, long observation times, and a lot of luck to pick out our emissions from the noise. They would also have to decide that a faint, messy, 100-year-old radio shell is interesting enough to justify an insane Starship project. And remember the time delay. Even if they detect those early TV and radar signals right now, and they are, say, 300 light-years away, they're seeing our world as it was 300 years ago. From their point of view, we're at the very start of the industrial age. No radio, no internet, maybe no obvious tech at all. If they wait until we're really bright in radio, we're already thousands of years into their future. By the time they see it, and by the time they can arrive, we've moved on again. So the full picture looks like this. The target is tiny, it's moving, its star is moving, and its position can only be known with a delay that matches the light travel time. And its I exist signal is weak, short-lived, and shrinking. Meanwhile, every attempt to tighten your aim costs fuel and energy that you can't easily spare. In practical terms, targeting Earth from across the galaxy is more like steering to a clear, lit-up airport while the airport is being moved around. You can't pause the galaxy while you do your calculations. So even if a civilization beats the distance, the speed limit, the rocket equation, the deep space damage, the civilizational lifespan problem, and the materials limits, they still have to solve a navigation problem that fights them at every step. The farther away they start, the worse it gets. The more time passes, the less reliable their data becomes. By the time a mission launched on Earth coordinates gets here, Earth could be in a different orbital phase, a different climate state, or even gone. And we still haven't touched another key point. Even if they somehow nail the interception and arrive in our neighborhood at the right time, they still have to catch us during a very specific kind of phase, when Earth is actually habitable and when we, or any tech civilization, are actually here to notice what's happening. Because planets change over billions of years. Climates swing, stars brighten, and technological phases might be incredibly short blips. So the next question is, assuming a ship can, in theory, hit us, how likely is it that it arrives during the narrow, shifting window where Earth is both comfortable for life and home to a technological species that can even recognize what's happening? How do you time a visit to another world when even habitable and life-friendly are temporary states that drift and vanish on billion-year clocks? That's the next problem. The target is not just small and moving, the right version of that target only exists for a limited window. Stars don't stay the same from birth to death. Your sun, for example, has gotten roughly 30% brighter since life first started on Earth. As stars age, they slowly pump out more energy, which means the habitable zone, the region around a star where liquid water can exist on a planet's surface, creeps outward over time, step by step, over hundreds of millions and billions of years. So, any given planet doesn't get a permanent sweet spot slot. It gets a window. Early on, it might be too cold, frozen over with weak sunlight. Later, the star brightens and you pass through a range where water can be liquid and complex life can form and thrive on the surface. Keep going, and eventually the star gets so bright that the planet drifts into a slow greenhouse. Oceans evaporate, the atmosphere changes, and surface life gets harder or impossible. From the outside, aliens trying to pick Earth-like targets aren't aiming at fixed points. They're aiming at moving bands of habitability that slide across orbits and planets over deep time. A world that looks perfect at one era can be a snowball in another era, or a steam bath in a later one. If they decide to launch based on what they see now, by the time the ship arrives, the climate state might be different enough that the original reason for the trip is gone. And that's just looking at the star and the big slow trends. Zoom in on the planet itself, and things get even more unstable. Earth's climate history is not some smooth, gentle line. It's full of sharp swings. There have been severe ice ages where glaciers reached much closer to the equator. There have been super greenhouse phases with almost no ice at the poles. Asteroid impacts have thrown dust into the atmosphere and darkened the sky. Supervolcanoes have pumped gases into the air and triggered big shifts. Continental drift has rearranged ocean currents and wind patterns. Right now, you live in a relatively mild, oxygen-rich, stable phase, with temperatures and conditions that happen to be friendly to large land animals, oceans as you know them, and high-tech industrial societies. A million years ago, the configuration was different. A million years from now, barring deliberate control, it will be different again. Coastlines move, ice sheets come and go, sea levels rise and fall by tens of meters, sometimes more. So if an alien ship is launched based on a snapshot of Earth looking nice, it is betting that tens of thousands of years later, the planet will still be in a similarly nice phase. There is no guarantee. We might be in a deep ice age, or in a hot, humid, low oxygen state, or heavily engineered in ways that make the original reading meaningless. The exact version of Earth they aimed at is a temporary state, not a permanent feature. Now add the technological phase on top of all that. You, as a technological civilization, are a very recent phenomenon. Earth is about 4.5 billion years old. Humans have had radio technology, something that's clearly visible over interstellar distances with good equipment, for maybe 150 years. That's a tiny fraction of total time, on the order of 1 part in tens of millions. If advanced civilizations in general have similar patterns, then tech phases are brief spikes on long, mostly quiet timelines. You get a world that's just geology and simple biology for billions of years, then maybe, for a few thousand or tens of thousands of years, there's a species that builds radios, lasers, rockets, industrial systems, and then, for one reason or another, that phase ends or changes into something quieter and less visible. For two such spikes on two different worlds to overlap in time and also be close enough in space to see each other and respond is statistically brutal. Most of the time, either your world is quiet while theirs is loud, or both are quiet or both are loud but so far apart that they can't see each other in any useful way. Even nearby on galactic scales, like a few thousand light years, can be too far if the visible tech phase is short. Now, combine that with travel times. Say a civilization detects Earth's tech phase and decides to launch. If their ship, even with very advanced propulsion, takes 50,000 years to arrive, and your entire visible radio-shouting phase lasts only 5,000 to 10,000 years, they have to launch before you look clearly technological and still somehow arrive while you are. They would have to predict your rise before it fully happens or accept that by the time they arrive, you might already be gone or transformed into something unrecognizable. That's like sending a letter that takes 200 years to be delivered, hoping the address will still exist, the person will still live there, and they will still care about the message. Most of the time, the house is gone, the person is dead, or the city has been rebuilt in a totally different shape. In galactic terms, the odds are worse because both ends of the connection are changing on their own timelines. So even if aliens can travel, and even if they beat the speed, the fuel, the hazard, and the engineering problems, there is still this timing issue. They have to launch during a period when our planet is in a habitable climate state, and then also catch us during the thin slice when we are technologically active and interesting to visit, and also not already wiped out or completely self-modified. When you stack it all up, the window where a planet is both physically habitable and home to a tech civilization that can notice visitors is narrow in time. The window where another civilization is in the right phase, sees that, decides to act, launches, and actually arrives during your window is even narrower. So the full picture is this. The distances are enormous. The speed limit is strict. The fuel and engineering demands are brutal. Deep space is hostile. Civilizations have limited lifetimes. And on top of all that, the timing has to line up just right for a successful rendezvous. And still, even if someone manages that timing miracle, there's another deep problem waiting. the energy economics. Because when you run the numbers on how much energy it takes to move mass between stars and compare it to what you can do with the same energy at home, it starts to look less like grand exploration and more like throwing your entire power grid into a fire for bragging rights. At some point, you have to stop asking, can aliens do this? And start asking, why would they even want to? Because when you look at the energy bills for interstellar travel, the numbers don't just look bad, they look absurd. There's a simple way scientists talk about energy use for civilizations, the Kardashev scale. A Type 1 civilization can use all the power available on their home planet, all the sunlight hitting it, all the wind, tides, everything, roughly 10 to the 16 watts for an Earth-like world. Type 2 can use basically all the power of their star, around 10 to the 26 watts for a sun-like star. Type 3 controls something like the power of a whole galaxy, about 10 to the 37 watts. Humanity is nowhere near Type 1 yet, maybe around 0.7 at best on that scale. Now, plug that into starflight. Earlier, we talked about how accelerating a 1,000-ton starship to a fraction of light speed costs something like a year of total human energy use, and that's just one burn, ignoring inefficiencies. For a truly relativistic, well-shielded, fully equipped ship, the real cost climbs much higher, easily to planet-scale energy for many years. So think about what that really means. If we were somehow a true Type 1 and we spent hundreds of years worth of our planet's entire power output on one mission, that's like you spending your entire lifetime income and your kids' lifetime incomes and their kids too on one lottery ticket. Maybe you get something amazing, maybe you get nothing. Either way, you can't get that energy back. For a Type 2 civilization, the numbers are less dramatic, but the logic is the same. Suppose you can tap a significant fraction of your star's output. You still have to decide how to use it. Do you pour that power into pushing a single ship to another star, or do you stay home and build big? Because with the same energy you'd burn on one serious relativistic starship, you could build huge orbital habitats in your own system, ring-shaped cities, free-floating colonies, giant mirrors to control climate, or the first pieces of a Dyson swarm, a shell or cloud of structures that captures a large fraction of your star's light. Those options give you guaranteed returns, more living space, more resources, more computational power, more everything, right where you are. Sending a ship to another star, especially to some random planet like Earth, is the opposite of that. It's a high-cost, high-risk side quest. You sink enormous power and material into a mission that might fail in transit, might arrive at a dead world, might find nothing useful. And even if it succeeds, it brings back information you could probably have gathered more cheaply with telescopes and small probes. And once a civilization gets powerful enough to even think about Type 2 or beyond, another option opens up that hits travel where it hurts. Why visit at all when you can just simulate? If you can harness star-level or galaxy-level energy, you can also run absolutely huge computers. With that much compute, it's probably easier to build ultra-detailed simulations of life-friendly environments, entire virtual planets with complex climates, ecosystems, and intelligent agents, than it is to build giant physical ships and push them across real space. For each unit of energy, a simulation can give you countless experiences, experiments, and scenarios. You can run many versions in parallel, rewind, tweak conditions, explore possibilities. Real-world travel, by comparison, gives you one shot. You launch, you wait, you get whatever reality actually has waiting at the destination. The cost per experience is enormous compared to virtual exploration. In that kind of future, physical star travel becomes the weird niche hobby, the equivalent of extreme mountaineering, not the main activity of a rational, resource-aware society. Most minds stay home in optimized environments, virtual or physical, because that's where the return on investment is best. And that's the key phrase here, return on investment. You can look at interstellar missions as giant, multi-generational investment projects. They consume a large fraction of your industrial output and energy capacity for a long time. They expose you to catastrophic failure, a drive malfunction, a collision, a design flaw. They require ongoing social support. What do you get back? Realistically, even a very successful mission gives you detailed data on a few systems, some rocks, maybe some new chemistry, maybe microbial life, maybe, if you are extremely lucky and the timing is perfect, a technological civilization that's still around. That's it. You don't bring back huge new energy sources because it's cheaper to build collectors at home. You don't bring back bulk matter because it's crazy to haul it across light years. So if you're a planner in that civilization, running the numbers, stacking up options, your spreadsheet looks brutal. On one side, spend this energy building habitats and infrastructure here, guaranteed benefits, low risk, fast feedback. On the other side, spend this energy on a ship that takes tens of thousands of years to arrive, probably finds nothing we couldn't model, and might not even get a usable signal back to us. Most advanced societies, especially ones that have already learned to manage big risks, probably look at that trade-off and say, no thanks. It's not that they can't possibly do it, it's that it's a terrible deal. So when you zoom out and look at the big picture, the interesting question isn't, is it physically possible for aliens to visit Earth? The numbers say yes in a very narrow, extreme sense, if you pour in insane amounts of energy and perfection. The more relevant question is it worth the cost compared to all the other things they could do with that energy? And when you put all the constraints together, the math screams probably not. For the vast majority of civilizations, for the vast majority of time, interstellar tourism just doesn't make sense. Information can be gathered remotely, experience can be simulated, and resources are better spent locally. But up to now, this has all been reasoning, equations, and scenarios. There's another way to test the idea. Look outside and see what the universe actually does. If starfaring empires and casual interstellar travel were common, the sky should look different. We should see evidence, not just in stories, but in data. Strange signals, artificial structures, signatures of massive engineering. So the next step is simple and unnerving at the same time. When we point our telescopes and radio dishes at the sky, what do we actually see? And does that match a galaxy full of visitors or a galaxy where almost nobody goes anywhere? Right now, you're sitting on a planet that's been quietly asking the universe a simple question for decades. Is anyone out there? And the answer so far, across all the data, is a very loud nothing. We've been listening. SETI and similar projects have pointed radio telescopes at huge patches of sky, staring at frequencies where our own transmitters are strong, the bands where a civilization like ours would naturally leak energy or choose to shout on purpose. What shows up in the receivers is not empty. You get pulsars ticking like precise clocks, quasars blasting energy from the centers of distant galaxies, weird one-off flashes like fast radio bursts. All of that is loud, energetic, and completely natural. What you don't see is the clean, obviously artificial hello you'd expect from a galaxy full of chatty neighbors. No repeating narrowband signals with clear patterns. No slow, deliberate beacons that look like someone is trying to get noticed. The universe is noisy, but it's the noise of physics, not the noise of conversation. You could say, okay, maybe they don't talk on radio, maybe they just build big things. Wouldn't we at least see the hardware? That's the next check, and it doesn't look promising either. Astronomers have surveyed millions of stars in visible light and infrared, looking for signatures of major engineering, things like Dyson spheres or Dyson swarms, structures that would block or re-radiate a star's light in strange ways. You'd expect stars partly wrapped in solar collectors to have odd brightness curves, or to glow more in infrared than a normal star of the same type because waste heat leaks out. There are a few stars with weird light curves where brightness dips in strange patterns. For a while, people got excited about those, but every time we dig deeper, the simplest explanations stay natural. Dust clouds, odd disks, overlapping objects. Nothing we've seen so far clearly demands this is a Type 2 civilization doing mega engineering. If advanced aliens were casually building star-spanning infrastructure, we should see at least a handful of very obvious outliers by now. Instead, we see a sky that mostly behaves like standard astrophysics. Maybe they're subtle, you might argue. Maybe they're not building big shells, but they still leave some kind of footprint in the data, something that screams technology, not star. So far, though, all the strong, clear signatures we detect are natural. We see gamma ray bursts, giant explosions from collapsing stars. We see supernovae, where stars blow themselves apart. We see gravitational waves from merging black holes and neutron stars. We see the flicker of accretion disks around black holes, the glow of hot gas between galaxies, all following known physical rules. What we don't see is obvious techno-signatures, no narrow laser beams sweeping across our field of view in repeated patterns, no modulated neutrino beams that switch on and off in coded way, no strange persistent signals that sit on one spot in the sky and refuse to match a natural source. That doesn't prove aliens don't exist, but it strongly suggests they're not out there behaving like our early science fiction expected, blasting out signals and covering their stars with hardware. So you have this mismatch. The galaxy is huge. The number of stars is enormous. The physics of star travel, while brutal, is not strictly impossible. And yet, when you look, you see nothing that clearly looks like someone is doing it. That silence becomes data. One explanation is that technological civilizations are extremely rare. Maybe life itself is hard. Maybe complex life is rare. Maybe intelligence is rare. In that case, the sky is quiet because there just aren't many players, and none of them overlap with us in time and distance. Another possibility is that civilizations don't last long at the technological stage. They reach radio, rockets, maybe basic spaceflight, and then hit self-inflicted problems, war, climate damage, resource collapse, or something we haven't even thought of yet. Their loud, visible phase burns briefly and then goes dark, leaving behind worlds that look normal again from far away. In that case, the universe is a graveyard of past attempts, with almost no one left in the broadcast and travel phase at any given moment. A third option is that long-lived civilizations do exist, but they don't expand aggressively, don't shout, and don't send big ships around casually. They might decide early on that it's safer to not advertise, or that starflight is a bad investment compared to building up their home system, or that any species that races to colonize everything is a threat best avoided. So they stay quiet, or communicate only in ways that are hard for us to detect, and rarely, if ever, bother with large-scale, obvious projects that would light up our telescopes. All three of those possibilities point in the same direction. Whether aliens are rare, short-lived, or deliberately quiet, they are not filling the galaxy with the kind of obvious noise and traffic we'd expect if interstellar visiting were easy, safe, and routine. No armadas, no glowing artificial shells around stars, no constant "we're here" beacons sweeping past us. So the silence itself becomes a clue. It lines up with everything you've seen so far in this argument. The monstrous distances, the hard speed limit, the punishing rocket equation, the lethal environment between stars, the limited lifetimes of civilizations, the narrow timing window, and the ugly energy economics. When you put it all together, the emptiness of the cosmic radio conversation isn't just eerie, it's supporting evidence. It says that, in practice, visiting other stars is not something anyone is doing at scale. Not because nobody wants to, not because curiosity doesn't exist, but because the universe makes it so hard, so expensive, and so low return that almost nobody chooses to. And even if a few extreme civilizations ignore all that and still push for star travel, there's another layer pushing them to stay home, one that hits even deeper than energy or risk: biology, ecosystems. The fact that living systems, as we know them, are tightly tuned to their home environment and do not move easily across worlds, let alone across different branches of biochemistry. If taking your own body, your microbiome, your food chain, and your entire support ecosystem through all of this is a nightmare, does it really make sense to land on a planet like Earth at all, when every cell in you is an experiment in a foreign chemistry set? How do you take a body built for one planet and drop it onto another without everything going wrong at the microscopic level? You don't. That's the next trap. Biology and ecosystems are tuned for home, and they really don't like to travel. Every complex organism, including you, is not just one creature. You're a walking ecosystem. Your gut, your skin, your lungs, your mouth, all are loaded with bacteria, archaea, fungi, viruses, all interacting with your cells, your immune system, your food. That whole invisible community is adapted to your chemistry, your diet, your environment. Now picture an alien. Same deal. Their body carries its own microbiome, a full suite of microbes that help digest their food, regulate their immune system, maybe even produce vital chemicals they can't make themselves. Take that package and drop it into a completely new world, where the atmosphere, the soil, the local microbes, the chemistry all come from a totally different origin story. You have no reason to expect it to play nice. Even on Earth, with one shared biochemistry, invasive species can wreck entire ecosystems. Rabbits in Australia, zebra mussels in lakes, plants, insects, pathogens, they move to a new region and everything there has to scramble to adapt. That's with shared DNA patterns, the same amino acids, the same basic cell machinery. Across different planets, maybe even different biochemistries, the interaction is a roll of the dice you really don't want to throw. So then, you might say, fine, maybe their biology and ours don't interact at all, maybe they're so different that nothing happens. Is that actually safer, or just a different kind of dangerous? It's very possible alien life doesn't use the exact same building blocks you do. They might use a different set of amino acids to build their proteins, maybe the mirror image versions of ours, different chirality. They might rely on a different sugar backbone in their genetic material, or even use a different solvent than water in some environments. That could make our pathogens unable to infect them, and their pathogens unable to infect us, because the basic docking mechanisms don't match. But it also means the food here isn't really food for them. If our proteins are made of the wrong-handed amino acids, their enzymes might not be able to break them down at all. Our fats might be the wrong shape, our carbohydrates might not fit their metabolic machinery. To them, Earth could be chemically rich and nutritionally useless, full of stuff that looks good on a spectrometer, but might as well be rocks in terms of digestibility. And the environment itself could be toxic. Trace metals, atmospheric gases, organic molecules in our air and water, all of that is tuned to what Earth life can handle. A different biology might find our oxygen levels corrosive, our atmospheric chemistry destabilizing, or our trace compounds lethal over long exposure. Even if we can tolerate them in hazmat suits, they might need something far more extreme just to walk around. So a landing isn't just get down, look around, say hi. It's a delicate experiment in cross-biochemistry where a single bad interaction can mean poisoning, starvation, or long-term health damage for the crew. But maybe they dodge most of that by not relying on the planet at all, and just take their own ecosystem with them, a fully closed life support loop on the ship. Does that fix things? This is where real engineering history says no, not easily. We've actually tried building sealed ecosystems on Earth. Biosphere 2 in Arizona is the classic example, a big closed habitat with soil, plants, animals, and humans meant to run on recycled air, water, and nutrients. It struggled just to keep oxygen and carbon dioxide in balance over a couple of years. Unexpected chemical reactions in the concrete, soil changes, and microbial activity drove oxygen down and CO2 up. The system lurched into weird states that were hard to control. That was on Earth, with gravity, easy access to spare parts, a normal magnetic field, and rescue crews right outside. Scale that problem up to a starship running for centuries in microgravity or artificial gravity, with cosmic radiation constantly nudging genetics and chemistry, and you see how fragile this gets. The balance between plants, animals, microbes, and chemistry has to hold not for months but for hundreds of years, with no open a window option if something swings out of range. Air needs to be scrubbed and recycled, water cleaned and reused, nutrients recovered and distributed, waste broken down and turned back into usable forms. Every step is a possible failure point. Filters clog, pumps jam, organisms evolve or die off, key species crash and take the whole food web with them. If your closed ecosystem swings too far, you don't get a second chance. The entire crew is locked inside the same experiment, with no backup habitat a few kilometers away. So even if aliens are better than us at ecological engineering, they still have to deal with the same basic constraints: conservation of mass, conservation of energy, the complexity of real biological systems. A closed loop that stays perfectly stable for centuries is not just hard, it's near perfect, and nothing in biology is naturally perfect forever. And under all of this, there's a deeper bias you can't ignore: the way evolution actually works. Evolution doesn't care about starships. It doesn't care about curiosity, exploration, or philosophy. It optimizes for one thing: survival in the local environment. On Earth, every species that's ever existed adapted to a niche, a specific range of temperatures, foods, predators, disease pressures, and physical conditions. Intelligence is just one more adaptation. It's useful because it helps you solve problems in your niche, exploit resources, and survive changes. It doesn't automatically come with desire to leave the planet or ability to manage a closed ecosystem in deep space for 1,000 years. The default outcome for an intelligent species, statistically, might be this: they become very good at reshaping their own planet and their own solar system. They build cities, satellites, maybe large orbital structures, maybe even spread across their local worlds. They solve local survival problems. They optimize their home. The jump from that to risk the entire crew and a huge chunk of our civilization's resources on a mission to a different star through hostile space into a totally unknown biosphere is not a natural next step. It's an extreme, optional side path that evolution never directly prepared them for. Any species that chooses that path is going against billions of years of selection for stay near the food and conditions that already work. So when you put this biological layer on top of the physics, a pattern emerges. Even if aliens exist, and even if they can, in principle, solve the engineering and energy problems, everything about their bodies, their microbes, their ecosystem, and their evolutionary history pushes them to stay close to the environment that built them, or to recreate that environment in controlled ways nearby. It's much safer and much cheaper to keep your biology where it's comfortable and explore the universe with sensors, robots, and signals than to drag your fragile wetware across light years and roll the dice on a chemically alien world. And that leads directly into the next point. If moving mass between stars is this expensive, this risky, and this biologically hostile, but sending information is basically just pushing photons, then the real action in a galaxy of minds won't be in giant ships at all. It'll be in beams of light. So the question shifts from why don't aliens visit to, if they're smart, why wouldn't they just talk from a distance instead? When you compare how hard it is to move stuff with how easy it is to move information, it starts to feel like the whole universe is screaming at you: stop sending ships, just send light. Moving a starship is expensive in the most basic way possible. You have to push mass. You need engines, fuel, shielding, structure, life support. All of it has weight. Accelerating even a modest 1,000-ton ship to a serious speed means dumping in mind-bending amounts of energy into it. We're talking entire planet's energy usage for a year just to get it going at a decent fraction of light speed, and then you still have to slow it down again. Now compare that to sending a signal. A 1 megawatt radio transmitter, which is big but not insane by our standards, can throw a focused beam across light years. The energy cost per bit of information is tiny. You flip electrons in an antenna, you push photons out, and they just go. For the same energy it takes to nudge a starship by a few meters per second, you could talk to half the nearby galaxy for ages. So, from a cold engineering point of view, starships are the worst way to communicate and photons are the best. There's a deeper advantage too. Information rides on light. Light, radio, X-rays all move at about 300,000 kilometers per second, around 186,000 miles per second. You don't accelerate photons up to that speed. They're born there. You don't need to shield them from radiation. They are radiation. You don't feed them. You don't keep them sane. You don't worry about their microbiome. If an alien civilization wants to interact with anybody else, the rational first step is not build a giant ark, fill it with fragile bodies, and hurl it into lethal space for thousands of years. The rational first step is build big transmitters, powerful receivers, and maybe a network of small robotic probes that can go places slowly while we talk fast with light. A probe the size of a car, or even the size of a smartphone, is orders of magnitude cheaper to move than a full crewed ship, and a bare signal, just data on a beam, is cheaper still. You can send maps, music, language, science, culture, all encoded in radio or laser pulses, and let the other side decode it at their own pace. So it's entirely possible that the galaxy already has a standard mode of interaction, and it's not starships. It could be a culture where civilizations only ever exchange information, and maybe tiny autonomous probes, and never bother with large crewed vehicles at all. From that viewpoint, your entire fantasy of aliens landing on the White House lawn is missing the point. From their side, we might already be cataloged. A tiny probe might have passed through the solar system a million years ago, took a detailed snapshot and beamed the data home, or high-sensitivity telescopes might have mapped our atmosphere for signs of life long ago. Once they have enough information, they don't need to send the ship here, because every additional bit of knowledge costs less if you get it with photons rather than rockets. And if they do decide to send anything physical, it makes more sense to send gram-scale or kilogram-scale robotic devices, not 1,000-ton hotels. Little machines can survive higher accelerations, tolerate worse conditions, and don't complain if the trip takes 10,000 years. From a resource perspective, big crewed starships look like prestige projects, not sensible infrastructure. There is one more catch for us specifically. Even if the galaxy prefers to talk with light, we might just not have been loud enough for long enough yet to show up on anyone's radar. Your radio bubble, the region of space that has actually been touched by your strongest artificial signals, is only about 100 light years in radius. That's how far roughly 100 years of radio, TV, and radar leakage can travel at light speed. The Milky Way is about 100,000 light years across, so your bubble is a tiny dot, a 1,000th of the galaxy's diameter, an almost invisible speck on the full map. Inside that bubble, your early transmissions are weak and messy by the time they arrive. Noise from stars, gas clouds, and other sources is always there in the background. Outside that bubble, you don't exist yet, as far as light-speed communication is concerned. Civilizations more than 100 light-years away literally cannot have heard from you yet, even in principle. On top of that, as we said earlier, you're getting quieter in radio, not louder. More fiber optics, more low-power cell towers, tighter beams, less raw leakage. Your peak hello moment in radio might be behind you. If aliens are scanning, they either haven't had time to hear you yet, or they see you as a faint, brief flicker that hasn't justified a reply, especially if they use long timescales to decide what's worth answering. So when you put all this together, the equation shifts. Physical travel is brutally hard, slow, and expensive. Photons are fast, cheap, and simple. Probes are cheaper than people. Our signal is small and recent. From a rational, high-tech alien point of view, the least likely way to interact with us is to send a big ship full of actual bodies all the way here. If you ever do get contact, the odds are much higher it'll be a faint pattern in radio, or a sharp artificial laser pulse, or a tiny probe drifting through the outer solar system, than a giant craft hovering over a city. And that brings up a darker angle. If the smart move is to stay home, talk with light, and maybe use small probes, then any civilization that insists on sending big, loud, obvious ships might be the reckless kind, the type that doesn't care about costs or risks or how it looks on someone else's sensors. Those might be exactly the neighbors you don't want showing up. which leads straight into the next filter. Before most species even get to the point of deciding between starships and signals, they have to survive their own technology. They have to get through the phase where they can build nuclear weapons, wreck their climate, or engineer pathogens without wiping themselves out or collapsing back into silence. So the final big question is, even if travel is technically possible, how many civilizations actually survive their own power long enough to try it? And how many decide that staying quiet is safer than being seen? How many civilizations get just smart enough to build starships right before they get smart enough to wipe themselves out? That's the next brutal layer. Intelligence doesn't just unlock space, it also unlocks self-destruction. Look at your own track record. As soon as humans got advanced industry and complex technology, you didn't gently slide into a peaceful golden age. You went straight into nuclear weapons, mass pollution, climate disruption, habitat loss, and the ability to wipe out entire ecosystems. Within about a century of serious industrialization, you had the tools to end your own story. That's fast. It's very plausible that this isn't special to humans. Intelligence is a way to grab more energy and resources, faster than instinct and simple tools can. Any species that evolves big brains and complex tech will learn how to control fire, then chemistry, then high-density energy like fossil fuels or nuclear reactions. The same knowledge that gives you rockets gives you bombs, reactors, and geoengineering. So a lot of civilizations might hit a wall right at the moment they become visible. They reach the stage where they can, in theory, build starships and big transmitters, but they also reach the stage where their mistakes can cascade into self-inflicted catastrophe, nuclear war, runaway climate change, engineered plagues, or AI systems that don't behave as intended. If they don't stabilize quickly, they don't last. The industrial phase is especially dangerous because of how concentrated it is. The tools you need for spaceflight, fossil fuels, high energy per kilogram, advanced manufacturing, global supply chains, are exactly the tools that let you overheat your atmosphere, strip your biosphere, and destabilize the systems you depend on. Think about the time window. The gap between we can maybe build interstellar probes and starships in a few hundred years, and we might seriously screw up our planet beyond easy repair could be tiny, a few centuries, maybe less. That's nothing on cosmic timescales. If most species stall out, collapse, or reset during that window, very few ever get to the point where they're calm, stable, and rich enough in energy to consider multi-millennial missions. This is where the idea of great filters comes in. When you look at Earth's history, life appears relatively early, within the first billion years or so, but complex multicellular life doesn't show up until much later. Intelligence, in the sense of tool-using, culture-building species, is even later. Technological civilization, with industry and global networks, is just the last tiny slice. So that suggests there might be several filters along the way. First filter, does life arise at all? Second, does it evolve into complex multicellular organisms? Third, does any of those lineages develop high intelligence and technology? Fourth, does that technological phase avoid wiping itself out and become stable, long-lived, and careful with its new power? Interstellar visitors, the kind that can cross light years and survive, require you to pass every one of those filters, and then, on top of that, decide that actually traveling to other stars is a good idea. If any one of those filters is very hard, or if many are moderately hard, the final number of civilizations that make it all the way through stay small. And even for the ones that survive their own early chaos, there's another angle: strategy. Once you understand how dangerous other civilizations could be and how visible you are when you travel aggressively, it might actually be rational to avoid going out and planting flags everywhere. Any species that loudly colonizes, builds big structures, and beams powerful signals in all directions advertises its presence. If there are other players in the galaxy who are not friendly or who are paranoid, that might be the worst possible move. The safest civilizations would be the ones that don't shout, don't expand in ways that are easy to see, and definitely don't rush to land on every promising planet they see. So, over time, the selection pressure might favor quiet, cautious strategies. The loud, expansionist, let's conquer the stars types either get noticed and eliminated, or they run into enough disasters that they tone down. The ones that last are the ones that learn to stay low, manage their risks, and focus on home optimization rather than interstellar adventures. From that perspective, visiting a place like Earth with a big, obvious ship is not just expensive, it's potentially suicidal. You drop into an unknown gravity well around an unknown biosphere in full view of anyone watching that region. You expose your tech, your biology, your tactics, all in one move. If there's even a small chance that someone more advanced is monitoring for exactly that kind of behavior, the rational move is to avoid it completely. Put all of this together and you get a very different picture from the simple sci-fi one. Even if star travel is physically possible, and even if a few species can solve the engineering, the survival strategy that actually works long-term may strongly select against big, flashy, crude interstellar missions. The ones that survive don't visit. The ones that visit don't survive. So by the time you reach a stable, wise, long-lived civilization, you've probably already passed through the filters and picked up a hard lesson. Don't take stupid risks with your only home. Don't burn ridiculous energy budgets on low-return projects, and don't wander into other people's gravity wells unless you absolutely have to. And that brings us right to the last practical barrier. Even if an alien ship makes it here, beats the distances, the physics, the hazards, and the filters, does it actually make sense for them to land on Earth at all? Or is that the point where a sane crew says, stop, we stay in space, we watch from a distance, and we never go down there? You've seen how hard it is just to get here, but there's one more catch. Even if a ship reaches our neighborhood, dropping down to Earth is the worst part of the whole trip. Cruising through interstellar space is one thing. Diving into a gravity well is a completely different level of risk. If an alien ship arrives somewhere near the sun, it can sit out in deep space with a comfortable speed and a lot of safety margin. Out there, small course corrections are cheap. If something starts to go wrong, you have time to react. The moment you decide, let's go down to that planet, you sign up for another huge change in speed, what rocket people call delta V, the total velocity change you need for a mission. To enter orbit around Earth, then go down to the surface, then get back into orbit and escape again, you need a big stack of delta V on top of the insane speed you already paid for just to reach the solar system. That means more propellant, more engine power, or some very aggressive use of aerobraking in the atmosphere. All of those are dangerous. From a mission planning point of view, it's often just cheaper and safer to stay in deep space, observe from there, and never commit to dropping into a gravity well at all. And the gravity isn't even the only problem. Earth has an atmosphere. For you, living down here, it's just air. For hardware coming in at orbital or interplanetary speeds, it's a wall. When you re-enter from low Earth orbit, you're moving at about 7.8 kilometers per second, roughly 28,000 kilometers per hour, around 17,500 miles per hour. Even at that speed, you get brutal heating. The air in front of the vehicle compresses and glows. Plasma forms. Surfaces reach thousands of degrees. You need heat shields, precise angles, and carefully planned trajectories to avoid burning up or bouncing off into space. Miss the corridor by a few degrees and either you skip out into space again or you dump too much heat into the structure and it fails. Aliens trying to land here face all of that, but worse. They might be coming in from a much higher solar orbit speed or from a weird trajectory. They don't have the luxury of decades of local test flights. They have to model the density of our atmosphere, the exact composition, how it changes with altitude, where the jet streams are, how the magnetic field interacts with plasma, all for a planet they have never physically landed on before. Your own space agencies on your own world, with detailed measurements and years of practice, still treat atmospheric entry as one of the most dangerous parts of any mission. That's with known materials, known heat shield designs, and close tracking. An alien crew attempting it for the first time is basically running a high-speed, high-energy experiment with one shot and no backup. And that's just the mechanical risk. There's also the contamination problem, which cuts both ways. Any complex organism, alien or human, carries its own microscopic cloud of life, plus whatever chemicals and spores are riding along on its hull, its suits, its equipment. If they land on Earth, they risk forward contamination, dumping their biology into our biosphere. Maybe their microbes can't do anything here. Or maybe one of them happens to interface with our chemistry in a bad way and start spreading. Even a single synthetic compound, stable in our environment and not easily broken down, could cause trouble. At the same time, they risk back contamination. Our microbes, our spores, our weird organic molecules get onto their hull, into their airlocks, onto their suits. When they go home or dock with another habitat, they drag those unknown agents into their own biosphere. If their immune systems and ecosystems are not ready for Earth-style chemistry, that could be catastrophic. If they're serious scientists, they'll treat Earth more like a delicate petri dish than a playground. You don't just stick your finger into a carefully prepared lab culture and stir it around. You observe from outside the container. You use remote instruments. You sterilize probes. And if they're serious about protecting their own world, they absolutely do not want random alien molecules hitching a ride back. That alone is a strong reason never to land a crewed vehicle on our surface. Once you look at it that way, the rational move becomes obvious. If they ever come this far, they send tiny sterilized probes. They stay in high orbit or even out at the edge of the system. They use telescopes, spectrometers, maybe atmospheric skimmers that burn up after collecting data. Full-scale landings with big ships and living beings are the highest risk, highest cost options on the table. From their perspective, the risk stack looks like this. Enormous energy cost to get here, long exposure to deep space hazards, major navigation challenges, then a final decision. Either stay in space and stay safe, or dive into a deep gravity well wrapped in a thick, unpredictable atmosphere, and accept contamination in both directions. One route lets you gather almost all the science and information you need. The other route adds huge danger for very little extra gain. So even in the extreme scenario where aliens are in our solar system, watching, mapping, maybe even sampling, there is still a very strong reason for them not to touch the ground. Staying in orbit, staying quiet, staying clean is the smart play. By now you've stacked up almost every kind of barrier you can think of. Distance, speed limits, fuel, radiation, engineering, timing, economics, biology, strategy, and finally, gravity itself. Each one makes alien visits less likely. Together, they push the probability down so far that for all practical human purposes, you can treat aliens landing on Earth as something that might as well be impossible. But there's one last step to make this airtight, pulling everything together. You can't say in a strict logical sense that it's absolutely impossible for aliens to ever reach Earth. Physics doesn't forbid it outright. What you can say is that when you weigh all these factors at once, the universe is giving a very clear message about how often it will actually happen in reality. So the final piece is this. Once you step back and look at the whole chain, from the size of the galaxy to the gravity at your feet, what does it really mean in human terms to say aliens will never visit? So after all of this, what does it actually mean for aliens ever showing up here? Is it just hard, or is it for all practical human purposes off the table? Start with the physics, because that's the part nobody can vote away. Distance, the speed of light, the rocket equation, radiation, and navigation are all separate problems, but they don't hit one at a time. They stack. The galaxy is tens of thousands of light years across. The nearest stars are trillions of kilometers away. To cross those gaps, you're stuck under a hard speed limit, about 300,000 kilometers per second, and the closer you push to that, the more your energy cost explodes. The rocket equation punishes you for carrying fuel, punishes you for shielding, punishes you for every kilogram you add. Deep space throws radiation and dust at you the whole way. Navigation has to be done with stale information because your target's position is always old news by the time you see it. None of those by itself is a fully locked door. You can imagine insane engineering solutions, bigger engines, better shields, smarter navigation. But when you pile them together, every partial fix makes the others worse. More shielding means more mass means more fuel means bigger ships mean more energy means more waste heat and structure to radiate it. It's a web of constraints, not a single barrier. So even before you talk about living beings, culture, or economy, the pure physics pushes routine interstellar travel into a tiny corner of possibility space. Technically allowed, practically brutal. Now add biology and sociology on top of that, and the walls get even higher. Civilizations don't live forever. Species don't live forever. Motivations don't stay fixed for tens of thousands of years. A mission that takes centuries or millennia isn't just an engineering project. It's a bet that your society will stay stable, cooperative, wealthy, and interested in the same goal across an insane amount of time. Meanwhile, biological bodies and ecosystems are not built for endless radiation baths and closed-loop life support. Every extra year in deep space is more DNA damage, more stress on life support, more chances for ecological instability inside the ship. You can try to dodge that with cryosleep or uploads, but the hardware still sits in the same hostile environment and still has to survive. So even among the tiny fraction of civilizations that could build a starship, you have to look at a much smaller intersection. The ones that are both able to travel and willing to invest star-level resources into visiting this specific planet at this specific time instead of doing 1,000 more rational things at home. That intersection is probably tiny. Then you look outward and ask, what does the actual universe look like if star-faring empires are common? And the answer is not like what we see. When we point telescopes and radio arrays at the sky, we see natural phenomena everywhere. Stars, gas clouds, black holes, jets, explosions. We see pulsars ticking, galaxies colliding, gamma-ray bursts firing. But we do not see anything that clearly screams, this is a civilization using entire stars for power and moving mass around on a big scale. No obvious Dyson swarms that block or re-radiate starlight in a clearly engineered pattern. No super bright laser beacons repeating prime numbers at us from halfway across the galaxy. No regions of space that look artificially cleaned up or reshaped. As far as our current instruments can tell, the universe looks like a place where physics runs the show, and technology leaves at most a very subtle or very rare footprint. That doesn't prove nobody's out there, but it does strongly suggest that if they are not covering the galaxy in easy-to-see infrastructure, and they are not constantly sending giant ships around in ways that light up our sensors. The observational verdict fits a universe where visiting other stars is rare, careful, or practically non-existent. So where does that leave the idea of aliens ever reaching Earth? If you want a strictly logical answer, you can't say never. Physics allows edge cases. A sufficiently extreme civilization with absurd energy control, insane long-term stability, and the willingness to ignore cost could send something here. You can't rule that out with absolute certainty. But that's not how humans normally use the word impossible. In everyday terms, you care about energy, time, risk, motivation, and what the data actually shows. And on that level, the story is pretty clear. The distances are enormous. The speed limit is unforgiving. Engines get punished by the rocket equation. Deep space tries to kill you. Civilizations are fragile. Biology hates long missions. The energy economics are awful. The sky is quiet. When you stack all of that, the probability that someone not only exists, not only survives, not only solves the tech, but also chooses to spend star-level resources to send a crewed ship here now and then actually lands is so small that, for any realistic human planning, you can treat it as zero. If anyone is out there, they're probably wrestling with the same equations you are, seeing the same trade-offs and reaching the same conclusion. It's smarter to stay home, build up their own system, talk with light, maybe send small probes, and leave the idea of dropping by Earth in person in the category of wild romantic stories their own species tells itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.